So now let's consider some cases where we have external force terms, such as this h of t over here. Now we are going to begin by considering no friction. So again, you'll notice there's no friction term here. F is equal to 0, aka this is undamped. We'll talk about the friction terms later. And with this as our starting point, now we have to make a choice as to what we want this external force function to be. We can't solve this differential equation just in general for all possible h's. We have to make a choice. But what we're going to consider is a sinusoidal function. And specifically, we're going to make a choice of h so that when I divide by m here, notice this m turns into 1. So when I divide by m, I want the result here to be a cosine omega t. Now, this is going to be some value, some constant. Notice here we have a sine wave with a frequency, and this frequency we're going to refer to as the forcing frequency. It's the frequency of this external force that's being applied. Okay. Now notice what happens on the left side of the equation, though. Again, dividing both sides by m. When you divide k by m, you get omega naught squared. And so something recognizable shows up on the left side of the equation. So, all things considered then, this is the case that we're going to now study. Okay. Very importantly, in order to be able to get things done, we need to make an assumption about this forcing frequency. Specifically, I need to make sure that it's not equal to the natural frequency. That makes things different, which we will consider later. Okay, so with a differential equation to work with, a nice exercise for students to work on your own is to write down the homogeneous solutions, write down a particular solution. We have methods for these. In fact, we've already considered the homogeneous solutions in a previous discussion. And then, of course, the general solution is all of these homogeneous solutions plus all of these, well, excuse me, plus that particular solution that we found there. Okay. All right. Now, what do these functions look like? What do this plus that? What does these sort of functions look like? Well, they look like a lot of different things. There's a lot of different such functions depending on the values of these various constants, depending on C1 and C2, and what's A, and etc. Okay, so we're going to look at a special case just to get a general idea of what these sorts of functions look like. And specifically, we're going to look at an initial condition, starting with position equal to 0 and velocity equal to 0. And in that case, if you solve for C1 and C2, the solution turns into this. Okay, now again, I've skipped over a lot of details there. I think this would be a great exercise for students to do on their own. Everyone should do this. Make sure you can get these homogeneous solutions. Make sure you can derive this particular solution, and make sure that you can use these initial conditions to find the solution to the initial value problem that looks like this. Okay, that being said, now again, our whole goal was to figure out what these things kind of look like. And so we now want to study what does this look like. Well, good news, this is just a constant. So really all we have to worry about is what does this look like. What is a difference of two sine waves? What does that look like? Okay. So there's some nice trig here that most students that take Math 216 have not seen before. It's very, very useful at this time. And hopefully students have seen this before. This is the angle addition formula for the cosine function. And then connected to that, here's the angle subtraction formula, I guess you might call it, for cosine. So these are important identities, important for students to make sure that they know these formulas, especially here in Math 216. So make sure that you know this. Okay. And now, look what happens when you subtract one from the other. Very interestingly, in subtracting, those two terms cancel because they're the same. These just reinforce because of the minus sign, and altogether get a wonderful little result that a difference of two sinusoids is a product of two sinusoids. Very surprising. At a glance, one wouldn't have expected this. Really, really neat trig identity. Rarely is this discussed in high school trig courses, but it's important here, well, for obvious reasons, because this is the result of our differential equation. Now, there's a couple of important asterisks. In order for this to work, of course, we need for these two functions to have the same amplitude. These have to have the same amplitude so that these two terms will cancel in the subtraction. Importantly also, we need these to have different frequencies. These two frequencies have to be different from each other. Okay. All right, so that being said, now there are some similar identities that students can get. This is a side note. By instead of subtracting these from each other, if you instead add these two equations to each other, if you add that to that, then those cancel, and you get, again, a reinforcing product of two sine waves. Okay, different details, same basic structure. Likewise, if you use the angle addition formulas for sine instead of cosine, then depending on whether you add or subtract, you get different identities, all that have the same sort of rough feature showing that a difference of two sinusoids can be a product of two sinusoids, again, with certain conditions. Okay, all right, now, that having been established, let's apply that to our situation here. We're trying to understand this function. Right, from the previous page, this was our solution, except for the constant in front, our solution to our differential equation. We want to know what this looks like. We now have a means of understanding this difference of two cosine waves. Well, we're interested in the difference of two cosine waves, and so we're going to set a minus b equal to omega t, and we're going to set a plus b equal to omega naught t. And let's see what A and B would make that happen. In other words, if I want to use this identity up here, what would I have to pick for my A and my B in order for that to work? Well, not hard to solve for A and B in this little system. And you get this. Oh, and I seem to have left off. This is B equals that. Okay. So there's our A and our B. They go, oops, there, and there. And therefore our function turns into this. So the function we're trying to understand, the solution to our differential equation, is a product of two sine waves like this. Okay, now fine, so what does this actually look like though? What is a product of two sine waves? We're going to look again at a special case. We're going to consider what happens when omega and omega naught are approximately the same. Now importantly, they have to still be different. They can't actually equal, but I want them to be not very far apart from each other, just to amplify the effect of the kind of function that we're looking at. So that being said, again, we can view this, not unlike what we did in the previous example, as roughly speaking a sine wave with a slowly changing amplitude. Here's the oscillation. Right, if omega and omega naught are approximately the same, then this frequency here is, well, it's approximately equal to both of those frequencies. So this is an oscillation. And this is a slowly changing amplitude. The reason this is a slowly changing amplitude is because, keep in mind, omega and omega naught are approximately the same. that means that this difference is small. That means that this sine wave here has a very low frequency. Therefore, it's not changing very fast. So you can kind of view this as an amplitude which of course is changing, however slowly. Okay. And so what does that look like? What does it look like when you have an oscillation with a slowly oscillating amplitude? And here's the picture. This is what it looks like. And here's the slowly changing amplitude. That slowly changing amplitude, of course, is a sine wave. Right. The oscillation there, well, the oscillation, now this is a fast oscillation, so, oops. Like that. And when you multiply these by each other, you get something that looks sort of like this. So it's oscillating along with the green oscillation, but the amplitude, how much does it swing, is sort of controlled by the purple slowly changing amplitude. Okay. And so you get this picture. Which again is hard to reproduce, but that sort of thing there. Okay, so this is what our solutions look like. At least this is what some of our solutions look like. Okay, so I want to talk about the idea of a beat frequency. If you look at this function, you'd say that, well, there's a sort of a periodicity in here where there's a sort of a beat, and then maybe less, and then there's another beat, and then the amplitude comes down, and then the amplitude goes up again, and there's a beat. So you can see this frequency, this period, I should say, we're going to call the beat period. Okay. However, the beat period, very importantly, is not the same as the amplitude's period. Don't forget that the amplitude function is this. That is one period of the amplitude function. And notice that the amplitude period is twice of what is the beat period, thus giving us this observation here that the beat frequency is twice of the amplitude frequency. Well, we already know the amplitude frequency. The amplitude frequency is over here on the previous page. The amplitude frequency is omega naught minus omega over 2, absolute value, of course. And then multiplying that by 2, we get the absolute value of omega naught minus omega. Okay, so the beat frequency is the difference, the absolute value of the difference of the natural frequency and the forcing frequency. Nice little result. Of course, now, don't forget the actual frequencies. You got to divide by 2 pi. Nevertheless, it remains that the actual beat frequency is the difference, absolute value of the difference of the actual natural frequency and the actual forcing frequency. Okay. Okay, so let's talk about the physical intuition for this. Keep in mind that these frequencies are going in and out of phase. There's 2 frequencies in question. There's the oscillation, there's the actual up and down movement, and then there's the forces that are being applied to that up and down movement. So remember, we have a mass, let's say a cannonball, and it's on a spring, right, and it's moving up and down, thus the oscillation, but then we're also applying these external forces. So one point of view that you can take on why this is actually a pretty satisfying solution is that sometimes the oscillation is going in the same direction as the forces. Sometimes they're actually in phase. Sometimes, that is, while the cannonball is moving up, the forces are also up. And furthermore, that while the oscillation is moving down, the force is also down. This is one way to say this, is that the oscillation and the forces are in phase. And it's not surprising that if, as the cannonball moves one way, it's being pushed in that same direction, and if, as the cannonball is moving back the other way, it's being pushed back in that same direction, one would sort of expect the amplitudes to be increasing. Okay. On the other hand, sometimes, that's what we just talked about there. Sometimes, though, they're out of phase. The oscillation and the forcing frequencies might be out of phase. So what would that look like? Out of phase means that as the oscillation is moving up, the force is down. And then likewise, as the oscillation is moving down, then the force is moving up. In other words, in this case, the force is always moving to oppose the direction of motion. Well, in that case, it's actually intuitively satisfying that the amplitude would be decreasing. The external forces is always pushing against the motion, and so you would expect to get less motion. Okay, so that's a physical point of view, sort of a sanity check on our result. It's not a rigorous argument, but it makes the result that we've gotten satisfying. Okay. One last observation I'll make. Examples of beat frequencies. If you play two nearby notes on a piano, and of course, any student who's done this will recall that there's a sort of a rattling sound. It almost sounds like the piano might have like a loose screw in it somewhere, and that's not what's happening. What's happening there is when you play two nearby notes on a piano, what you're doing is you are creating two sine waves with similar frequencies. So you're creating a sound wave that takes a form that's pretty much what we've written down here. And from our analysis, a difference of two sine waves is a product of two sine waves, and the beat frequency of the created, this created resulting sound wave, the beat frequency is the difference of those two frequencies. And again, even if you want to talk about actual frequencies, the beat frequency is the difference between the two actual frequencies. So if you have two nearby notes on a piano, their frequencies are pretty close to each other. Their frequencies might only be a few hertz apart, maybe 10, 15 hertz apart, 10 or 15 beats per second apart. And so that means that the beat frequency would be a very, very low frequency, like 10 or 15 hertz. And that's not sound. That's something that would come off as a kind of a rattle. So that rattling sound that you hear when you play two near notes on a piano, it's not a rattle, it's the beat.